This lecture is part of a series of lectures on rings and modules and will be about tensor products of modules. It's a sort of continuation of the previous lecture. So the previous lecture we did tensor products of abelian groups, which are Z modules, and we're now going to look at tensor products of modules over other rings. First of all, we're going to do the case when R is a commutative ring. So what we want to do is we've got two R modules, M and N, and we want to have a tensor product which classifies bilinear maps from M times N to some other modules. So if we've got a bilinear map from M times M to C, we also have a bilinear map there, and this should sort of factorize via a linear map from M tensor N to our module C. And we can construct this in much the same way as we did for abelian groups, only there's one extra complication. So you remember for abelian groups we take M tensor N to be generated by elements M tensor N for Mn in M times N. And we should quote it out by some relations to make this map bilinear. So we have the relations A1 plus A2 times B equals A1B plus A2B. Sorry, that should be a tensor. And we have the relations A times B1 plus B2 should be equal to A tensor B1 plus A tensor B2. But we also need some other relations to force this to be R linear. So we also add the relation that RA1 tensored, so RA tensor B should be equal to R times A tensor B, and of course we have A tensor RB should be equal to R times of A tensor B. So these are the two extra relations that we need if our ring is not the integers. You notice that if our ring is the integers, then these relations just follow from the first one. So with that minor change, the theory of tensor products over commutative rings is pretty similar to the theory of tensor products over the integers. I'll just sort of work out one example. Suppose we've got an ideal I in the ring R, and we want to work out the tensor product of R over I with our module M. So what we do is we just choose an exact sequence for this module here, and we can have the rather obvious exact sequence. 0 goes to I, goes to R, goes to R over I, goes to M, goes to 0, and then we tensor this with M. Sorry, M shouldn't be there, that should just be a 0. And then we tensor this with M, and we get I tensor M maps to R tensor M, which is just M, and this maps to R over I tensor with M maps to 0. And notice this map here isn't necessarily injective because tensor products don't preserve injectivity. Well, it's not quite clear what I tensor M is, but its image in M is pretty clear. So the image of this map is just going to be IM. So we see from this that M over IM is isomorphic to R over I tensored over R with M. So we've worked out the tensor product of any module with any module generated by one element. Now let's take a look at tensor products of non-commutative rings. And you have to be a little bit careful here. So let's try a first attempt, which won't really work. Suppose we try just as before. So we define the tensor product of M over N to be generated by these things M tensored with N, modulo these relations we had, which are things like Rm tensor N should be equal to R of M tensor N, and so on. And the trouble is, if the ring is non-commutative, we run into unpleasant problems here. So here, suppose we take M and N to be left R modules. And then we have the following problem, because we have RSM tensor n should be equal to SM tensor Rn, and this should be equal to M tensor Srn. On the other hand, this should also be equal to M tensor with Rsn. And if we compare this with this, we see that our tensor product is going to be collapsing a bit too much. It sort of more or less forces the elements of the ring R to act in a commutative fashion on these modules. So that doesn't really work in a very satisfactory way. So we can have a second attempt. Let's take M to be a right R module and N to be a left R module. Then we can add in the relation MR tensor N is equal to M of R M tensor Rn. And now this works much better because we're not changing the order of any variables. You see, the problem is whenever you're working over a non-commutative ring, you don't want to switch the order of things. So here we're sort of switching the order of R and M, and this ends up causing complications. So if we do this, we're fine, but there's a problem. So we can define tensor product of M and N by adding the distributive relations in this relation here, but the problem is that M tensor over Rn is just an abelian group, not an R module. I mean, how are you going to act on this with R? If you try multiplying by R on the left with M, you can't do that because M isn't a left R module. If you try multiplying on the right, then you're going to get mixed up with this relation here, and it's again going to be a bit of a mess. So provided you don't mind the tensor product being an abelian group, this sort of works fine, but sometimes you want the tensor product to be an R module, and you can do this as follows. If we take M and N to be R bimodules, what this means is you can multiply M on the left and on the right by the ring R, and then everything works out fine. So you have the relation MR tensor N equals M tensor Rn, that's fine, and you can define the left action of R on this bimodule by saying R of M tensor N is equal to Rm tensor N, and you can define the right action by saying M tensor N times R is equal to M tensor NR. So for bimodules, the tensor product of two bimodules over R will be a bimodule, and everything works pretty much like the commutative ring case. Commutative rings is of course a special case of this, because any left module over a commutative ring can be made into a bimodule in a rather obvious way. So really, tensor products work better for bimodules rather than modules. Now let's give some applications of tensor products. So the first is a common one in differential geometry. So if we've got a vector space as V and W, and V has a basis V1, V2 and so on, and W has a basis W1 and W2 and so on, then V tensor over the field W is just another vector space with a basis Vi tensor Wj. So in particular we see the dimension of V tensor W is just the dimension of V tensor with the dimension, times the dimension of W. Now in differential geometry you often use this where V is the tangent or possibly cotangent space to a point, and W is the dual space. So what we do is we take a basis Vi for V, and we take a dual basis Vi star for the dual space V star. And then you might have elements of V tensor V tensor V tensor V star, say, which are going to be a sum over, it might be some sort of sum over things like, say, R, A, B, C, D of V, A star, let's take something on a dual base, times VB times VC times VD. So this would be a sum over all A, B, C, D running over from 1 to n. And differential geometers are kind of lazy, so when writing down elements of tensor products, they miss out the summation sign and they miss out all these basis elements and just write down a sort of letter with lots of superscripts and subscripts. Actually, when differential geometries work with things like this, they're really thinking of this as being a vector field, or rather a tensor field. So this will not be just a real number, it will really be a function on some manifold, and this will not represent just a single element of some tensor product, but will represent an element of the tensor product for each point of the manifold, and so on. So the tensors you get in differential geometry really are closely related to tensor products of vector spaces. Next application, we can look at coproducts of commutative rings. So suppose we've got two rings R and S. Then we can certainly form their product, R times S, in the usual way, which is universal for maps to R and S, but we'd also like to form a coproduct, and I'm going to write this as R tensor with S because that's what it will be. And what we want is this to be a sort of universal ring generated by R and S. So if we've got any homomorphism from R and S to some ring, there should be a unique map from this coproduct to it. And as is strongly suggested by notation, this actually turns out to be the tensor product. So we take the tensor product of R and S, considering them as abelian groups, and we define a product on this just by saying R1 tensor S1 times R2 tensor S2 is equal to R1 R2 tensor S1 S2. And then you can check this map is well defined using the universal property of tensor products, and you can then easily check that this is a coproduct of these two rings. There are some variations of this. For instance, you can take S and T, you can take R and S to be T algebras. So we've got a map from T to R and to S, and we want a universal ring. We want a universal T algebra generated by R and S, and not very surprisingly, we get the tensor product over T of R and S. So this is very heavily used in algebraic geometry because rings correspond to schemes, or at least to affine schemes. An algebraic geometer would sort of look at the corresponding maps of spectrum of rings and would get a diagram like this. So we get spectrum of R times over TS, and he would call this thing here the fiber product or pullback of these two affine schemes. And you can see an explicit example of this. Suppose we just take, let's take a field K, and let's take the ring of polynomials over K, and let's take the ring of polynomials over K in a slightly different variable. So this would be like having a point and having an affine line mapping to the point. And we want to know what the product of these two spaces is, and rather obviously the product is going to be the affine plane. And this corresponds to the tensor product of these two spaces here. And the tensor product is easy to work out because this has a basis 1x, x squared, and so on. This has a basis 1y, y squared. So this thing here, which is going to be k of x tensor with k of y, has a basis of elements x to the I tensor y to the j, which you might as well write as x to the I times y to the j, And you can immediately see that this is really just the ring of polynomials in two variables, which is indeed the collection of functions on the affine plane. By the way, we've got to be a little bit careful with this construction because the topological space here isn't the product of these two topological spaces. So you remember the spectrum of k of x, if k is algebraically closed, is basically a copy of k corresponding to ideals of the form x minus alpha union a point at a sort of generic point corresponding to 0, and the spectrum of ky is similar. We've got a copy of k corresponding to things like y minus alpha and a generic point. And if you take the product of this space and the product of this space, it indeed corresponds to a subset of the affine plane, because you've got points alpha beta kind of corresponding to the ideal x minus alpha y minus beta, and you've got a generic point corresponding to the ideal 0, and you've got vertical lines corresponding to a product of a point here and 0 here, and you've got horizontal lines corresponding to the other sort of product. But the trouble is the affine plane has lots of prime ideals other than these four. For example, the ring of polynomials in two variables has lots of other prime ideals. For instance, we could just take f of x y equals 0 for some irreducible polynomial, say y squared minus x cubed minus x equals 0. So there are loads of other points of the spectrum of this ring here that don't come from a product of a point in this spectrum and this spectrum. So the product of two affine lines being an affine plane is sort of more subtle than you might expect from analog with general topology. So the next application is representations of groups. And for simplicity, let's take G to be finite, and a representation is going to be G acting on a vector space V, and we'll take dimension of V to be less than infinity, and V is going to be over the complex numbers. You can do it more generally, but you get some extra complications. And now, if we've got two vector spaces acted on by G, we can take their direct sum. And this is acted on by G in a pretty obvious way. We just say G of V plus W is equal to G of V plus G of W. And we can also define the tensor product of these two vector spaces. And it doesn't take much imagination to see that G also acts on the tensor product. We can just define it in the really obvious way like this, and this just works just fine. So we can not only add two representations of G, we can also sort of multiply two representations of G. And you notice this behaves a bit like a ring. So V, U plus V tensored with W is equal to U tensor W direct sum V tensor W. And you can check that this holds as representations of G, and U tensor V tensor W is isomorphic to U tensor V tensor W, again as representations of G. And you can see these are looking very much like the axioms for a ring. So you can ask, is the set of isomorphism classes of representations of G a ring? And that means finite dimensional complex representations, of course. And the answer is not quite. There is no subtraction. There's no general way to take a vector space and subtract another vector space. Well, that doesn't really matter much. We can sort of force subtraction. So you remember when you construct the integers from the natural numbers, you kind of just sort of forcibly add the negative of any natural number, and with a bit of care you can make a ring out of that. And that's a construction you can do with anything that looks like a ring without subtraction. You can sort of kind of force it to be a ring. If you do this, you get something called the representation ring of a group G. I should just mention when you convert a ring without subtraction to a ring, you've got to be a little bit careful, because you can get phenomena that A is not equal to B, but A plus C is equal to B plus C in your ring without subtraction. This means that A and B become the same in the ring, even though they're not the same in the sort of semi-ring you start with. Anyway, let's just give a couple of examples of this. Suppose we take G to be a cyclic group of order n, and we can look at some one-dimensional vector spaces acted on by G. So suppose this is generated by a little element G. So we take V and W to have dimension equal to 1, and we might take G of V equals e to the 2 pi I A over n for V in V, and G of W equals e to the 2 pi I B over n for W in W. So there's two one-dimensional vector spaces acted on by G, and now we can take their tensor product, which will again be one-dimensional. And how does G act on it? Well, it's kind of pretty obvious that G acts as multiplication by e to the 2 pi I A plus B over n, because if you look at a vector V tensor W, G multiplies that by the first number and this by the second number, so it multiplies this by their product. So a second example, let's take a non-commutative group just for a change. Let's take G to be the group S3. And now we can see several different vector spaces acted on by G. We can have U, which is just C, with G acting trivially. And we can take a vector space V, which is C, and this time G can act as the sign representation. So you remember S3 has elements 1, 2, 2, 3, 3, 1, 1, 2, 3, and 1, 3, 2 of permutations. And this, in this 1, 2, 2, 3, and 3, 1 can act as -1, and the other elements act as 1. Or W could be a two-dimensional representation with G acting as symmetries of a triangle embedded inside a two-dimensional vector space. And now we can ask what happens if you tensor these together, and I'll just leave these mostly as exercises. If you take V tensored with V, this turns out to be isomorphic to U, because if these are acting as -1 on V, then they will act as 1 on V tensored with V, so we get the trivial representation. If we take W tensor W, this is a little bit more interesting. It actually splits as W plus U plus V, if I've worked everything out correctly. So in fact you find that these are actually, U, V and W are a basis for a three-dimensional ring over C. I mean, it's three-dimensional as a vector space over C. So this is the representation ring of the symmetric group S3. So representation theory of finite groups spends a lot of time trying to work out representations of other groups. I've actually got a series of lectures on representation theory that discusses this in more detail if you want to know more. So for the final example, we can do tensor products of fields. For example, this is used quite a lot in algebraic number theory. You might take the field of rational numbers, and you might take a field, say a quadratic extension. You might take, say, the ring of Gaussian rational numbers. And if you're into p-adic fields, this is also contained in, say, the two-adic number fields. And then number theorists are very interested in doing things like taking the tensor product of the two-adic numbers over the rationals with Q of I, and splitting this as a sum of fields, and that turns out to be the same as decomposing the prime 2 in the Gaussian numbers. Well, I'm going to do a somewhat simpler example so that I don't have to explain what the two-adic numbers are. I'm just going to take the complex numbers tensored with the complex numbers over the reals and ask, what is this equal to? Well, this is a basis 1i, this is a basis 1i, so this thing here has a basis 1 tensor 1, 1 tensor I tensor 1, and I tensor I. And it turns out that this actually splits as a sum of two fields, C plus C, and what we need to figure out are what are the identity elements of these two copies of C. And you remember, in order to split a ring, we need to find idempotents in it, and we can find some idempotents here. We get 1 tensor 1 plus I tensor I over 2, or we can have 1 tensor 1 minus I tensor I over 2, and these are both idempotents. So this copy of C is just C times this number, 1 tensor 1 plus I tensor I over 2, and this one is kind of similar. Okay, I think that's enough about tensor products.